Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering. Hello everyone, let us continue our discussion on this introduction to the mechanical behavior of materials, right. If you look at what we have seen so far, we looked at the stress at a point, and we also looked at a strain at a point in much more detailed manner. And then we also looked at the plane strain condition, plane stress condition, and so on. So then we moved on to elastic, I would say, stress strain relations, right, on the basis of linear elasticity theory. We looked at most of the simple relations and constitutive relations, and then from the constitutive relations, what are the other relations you can make use, you can derive involving various material constants like Young's modulus, shear modulus, bulk modulus, and so on, right. So we will just continue that, and so one of the constitutive law we have just seen is Hooke's law, right. I said that we have also looked at this Hooke's law in a more generalized form, right. So this generalized Hooke's law can be used to account for multi-axial loading condition as well as material anisotropy. Okay, very important point. Okay. Suppose we can clearly show that in a multi-axial condition, for example, any material subjected to different type of loading, I will just show up just in few slides later, I will show some general state of stress in a day-to-day life examples. So in such conditions, this generalized Hooke's law only is being used. Okay. So I will just recall this again, generalized Hooke's law. It can be written like this in a tensorial notation: epsilon ij is equal to S ij KL. Okay. There is a typo here, it is ij KL, not double j, ij KL and sigma KL, where S ij KL is a compliance tensor. Okay. Similarly, we can write for the stress sigma ij is equal to C ij KL times epsilon KL, where C ij KL is elastic stiffness. If you recall, we have just gave some introduction about tensor quantities, and this elastic stiffness we described that as a fourth rank tensor quantity. Okay, this is what it is. So we now know how many constants it will have, right. We just looked at the formula, right, 3 to the power n. So this is a fourth rank tensor quantity. Suppose if you expand, you would get 9 equations each with 9 terms. So total about 81 constants. That is what it is, elastic stiffness, right, in all. Since epsilon ij and sigma ij are symmetric tensors, only 36 of them are independent and distinct terms. So we have also introduced this terminology, symmetric tensor, right. So you don't have to worry about it. So we have just had some introduction about all these terms. So we will just see how these constants are evaluated, and this is for isotropic materials, all these relations. The situation is complicated greatly when the material is anisotropic, wherein the elastic constants vary as a function of crystallographic orientation. So this is very important point we have to remember. When the material exhibits anisotropic, that means even in a real material, you take a cubic systems, you all know that we mark different directions in a cubic system, whether it is simple cubic or body centered cubic, face centered cubic, you all might have undergone an exercise how to mark directions using Miller indices. So, if you recall all this, you also talked about material, not material, atom populated in each type of plane, right. For example, 100, what is the planar density, atomic packing density, and if you look at 111, what is the atomic packing density, and so on, 110 and so on. So, in each direction the packing density is going to be different, and similarly your the stiffness constant is also going to be slightly different. So, that is why we are talking about anisotropic material or anisotropic nature of the material, right. So, since this is the case for practically for all crystalline solids, it is important to consider a general loading condition as shown in figure. So, we have already seen this, this figure is most familiar to you now. So, this is a general case where we describe the state of stress in 3 dimension. We can consider this again. So, you have the 3 mutually orthogonal normal stresses, and then shear stresses are marked on the respective plane. And we see that there are 3 normal and 6 shear stress components. However, since tau yx and tau xy and tau yz is equal to tau zy and tau xz is equal to tau zx. So as to avoid rotation of the cube, only 6 independent stress components remain that determine the strain of the body. So, this also we have already seen, just we are going to just recall, because we are going to see what is this. So, the strains in the each direction may be given by these kind of equations. So, I am just giving you these equations not to just scare you or something, but you should understand what is that we are talking about. 81 constants, how it is coming to 36, and then how it becomes 6 normal stress and shear stress and so on, and how this equivalents are realized. So, you have this strains on each direction, and you see that it is each direction normal stress and the shear stress components, right. Totally you have about 6 independent stress components, right. So, all 6 are here. So, it is 6 is for each direction, right. So, where this Sij, you can see that S11, S12 and so on here, S11, S21, S31 so on, they are called elastic compliances. And you can express the same thing for stresses, right, because that is what linear elastic theory comfortably shows that. So, in terms of stress, these are the equations, and what is Cij? This is elastic stiffnesses, right. So, we can now think of using this relation for a real system. So, the reversibility of elastic strain leads to the fact that Sij is equal to Sji, and similarly Cij is equal to Cji, which reduces the number of independent material constants from 36 to 21. So, we have also looked at the similar reversibility in the shear stress condition, right. Similarly, in elastic stiffness and compliance coefficient also, the reversibility rule is applied, and which further reduces the independent constants from 36 to 21. This is the point you have to remember. As a result of symmetry consideration, the number of independent constants decreases further with 9 constants required to describe the elastic response of an orthorhombic crystal, 5 for hexagonal and only 3 for cubic material. So, life becomes simpler once you bring in lot more parameters which can be similar in all orientations. For example, symmetry. When you consider symmetry, it gives further reduction in number of independent constants. For example, for a hexagonal system it is 5 and only 3 for cubic system. Okay. So, for the later systems, the elastic compliance matrix reduces like this. Instead of 6 by 6, it is still remains a 6 by 6, but then you have lot of components become 0 because of the symmetry consideration. So, it is Sij is equal to S11, S12, S12 like this. Only these two stiffness constants, of course 3, S11, S12 and S44. These are the 3 constants which is able to describe the anisotropic nature of the crystal in a cubic crystal. So, it can be shown that for the case of cubic crystals, that the modulus of elasticity in any given direction may be given by the equation in terms of these 3 independent elastic constants and the direction cosines of the crystallographic direction under the study. So, this is the one expression we can use for finding out the I would say the anisotropy or the describing the elastic modulus in a simple cubic system. Okay, that is 1 by E is equal to S11 minus 2 times S11 minus S12 minus half S44 multiplied by L1 square, L2 square plus L2 square, L3 square plus L1 square, L3 square. This you know that what it is, direction cosine, right. So, what I was trying to tell you by giving all these things, we just got introduced to the linear elasticity theory, and then how it describes stress strain and its relation, and how it validates for an isotropic material, then what happens to anisotropic material, and how these elastic constants are evaluated. Just give you a feel of not just showing equation, but just you have a grip of how these equations are useful in real systems. So, that is what my intention. So, later probably you can do some problems involving this. We can calculate elastic modulus for particular given direction for different crystal systems. Then you will appreciate this concept much more easily. Okay, having gone through a lot of expressions for stress and strain and relation and so on, now we'll come to reality. I am just showing some of the real time applications where we can show the common states of stress. I have shown some very colorful picture here, and what is this equipment? This is a sky lift, basically a sky lift. We will just go through 1 or 2 components here and then try to understand what is the state of stress. For example, you see the rope here which goes through this pulley and drive this wheel, right. Similarly, this rope, and there is a rotating shaft here which rotates. Of course, when the wheel is rotating, this rod also will rotate, but we can just try to get some grip of what is the state of stress here. For example, this particular rectangular box which is showing this rope, what kind of stress it undergoes? It undergoes simple tension. Okay, it just pulls, right. It pulls, the drive wheel just rotates in this direction, so it just pulls. So, the rope is being subjected to a simple tension. Okay. So, this is what we describe a simple tension, and the wire will have a cross section, the cable will have a cross section A naught, and we know this expression, very simple expression, sigma is equal to F by A naught, and a simple tension. What about this shaft? Suppose this rotating shaft, this is a torsion, it undergoes simple torsion, a form of shear. Okay. So, we know now what is shear component of a stress, right. So, how do we describe them? This is what we describe them. This is a physical picture, a drive shaft of diameter 2r, and this is the moment, right, shear in this, and this is the cross section, and this is the notation we have already seen for how to represent the shear stress, right. So, this kind of notation is, if you recall, this is a positive shear stress. So, shear stress again shear force divided by area. Okay. So, this is a simple, I just want to give a feel of a real time application, a sky lift. Okay. And the next one, we will show some simple compression. You can see that this is a bridge, it is a hanging bridge. We can look at this small iron strips which is being connecting these two big structures, a curved structures and this linear structure. And there is another example. It is a rock, a huge rock sitting on this small pile up of a kind of a cliff here, which is there in this national park, and very nice photographs. But we can just think about element from this region and this rod, what kind of stress it undergoes. It undergoes a simple compression. So, we can represent this by this. So, compressive stress is a negative stress, right. So, that is why we look at this. And this is, what is this? This is a pressurized tank. So, just think about what kind of stress it can experience. So, pressurized tank experiences this kind of a stress force. What is this? They are all positive stress, but in both directions. That means biaxial, okay, biaxial tension. Okay, that is a real time. And what is this? There is a fish in the fish tank, okay, fish and or water, whatever it is. What it undergoes? Very nice picture. So, this is the symbolism. What does it mean? It undergoes a triaxial state of stress. Okay. What kind of stress? It is a compressive stress, okay, but in all directions. We also have another name for this. If it is, there is no shear term, what is that called? You just you have to recall, we have just shown the matrix also, right. So, this is hydrostatic stress, but it is in the compression mode. So, hydrostatic compression. So, like that you can just connect day to day applications or whatever you come across. You just think about what type of stress it undergoes. It will also give a very good feel for this subject, right. If you start thinking or connecting, you will not find it more mathematical or equation and so on. So, it will be interesting. Okay. So, now that we have described the kind of state of stress and strain, and we have looked at relationships, simple relationships, and now we go to properties, because at the end of the day, with all this knowledge, we should try to understand and relate these theories to understand the properties of the material. That is our aim, right. So, first we look at elastic properties. So, we have now gone through elasticity, now we will look at elastic properties. Okay. What are the elastic properties? You all have some idea about elastic properties. In a day to day life, you have n number of things which we use from every day, every material, right. It will undergo a lot of elastic deformation. Take some simple things like what I demonstrated in the introduction video. All materials change in shape, volume, or both under the influence of an applied stress or a temperature change. Okay. So, this is what we try to describe. Even if you remember, when I showed this Condon-Morse curve, right, where the potential well diagram, we talked about two things. One is potential energy, another is we related that curve to the force, and also we brought temperature into the discussion. That is because that also can influence interatomic distance. Okay, that's very important. That's why applied force and temperature change can bring a change in shape, volume, or both in any material. Very important. The deformation is called elastic if the stress or a temperature induced change in the shape or volume is completely recovered when the material is allowed to return to its original temperature or state of stress. So, this also you know very well now. Any material, any type of force you apply, irrespective of state of stress, or if you remove the force, if it retains its original position, then it is completely recovered, elastically got recovered, right? Elastic energy got recovered, something like that. And similarly, the temperature, right? We have, we can see in the future class some of the examples, right? Even a temperature dependent behavior, material behavior, for example, shape memory. They are all related to this, okay? So, in crystalline substances, the relationship between stress and strain in an elastic region is typically linear. Very important. Look at the statement carefully. In crystalline substances, the relationship between stress and strain in an elastic region is typically linear, whereas non-crystalline, that is long chain molecular materials, generally exhibit non-linear elastic behavior. So, it is not necessarily that stress is inversely proportional to strain, that is a linear relation, may not be valid for all kind of material. And now you know why we just started with a different kind of bonding and structure and so on. Now you see, the moment you change from crystalline to non-crystalline or long chain molecular materials, for example, polymers, this linearity is no longer exist. So, they exhibit non-linear elastic behavior. This is exactly shown in this two stress strain diagram. So, stress versus strain, and the material undergoes linear or response to the stress up to the point A. That means, beyond this point A, the material will no longer behave elastically. That is the limit. Okay. Similarly, you see that it is an interesting curve. So, it is not linear, but it is still an elastic region. It all the way up to point A, it undergoes elastic deformation, but it is non-linear. So, non-crystalline long chain molecular material will exhibit elastic behavior, but not linear behavior. Okay. So, yeah, this is what theory of linear elasticity try to explain this on atomic basis of the behavior observed, and deals with proportionality between stress and strain on a macroscopic scale utilizing elastic constants. So, this we will see what is that.